intro to our session on shape spaces and application of shape spaces. I've been told that we are very short on timing, so we have 5 talks, 20 minutes each, 3-4 minutes question after that. And I've been asked to really be merciless in the enforcement of timing, so please try to really stick to 20 minutes, 21 minutes. And we will have like a couple of minutes for question for every single talk. So without further ado, our first talk of the session is by Tomonari and Ushio Tanaka on the geometric properties of the textile set and the strict textile set. So.
Thank you very much. I am Tomonari from the University of Tokyo, Japan. And this is joint work with Dr. Ushio Tanaka. In this talk, I'd like to, first of all, I'd like to thank the organizers and the session chairs for making this nice conference. First of all, in this talk, the textile, we will investigate the textile set and the strict textile set, which are related to a data visualization tool called the textile plot, which is proposed by Kumasaka and Shibata 2008. And the textile set is a geometric object constructed for understanding the textile plot outputs. And today's talk, we find additional facts on a proper subset called the strict textile set, and also study some other properties about differential and analytical geometric properties. So let me remind you of the textile plot. What is the textile plot? The textile plot is, the textile plot transforms a given data set or data matrix consisting of continuous and categorical variables into a real valued matrix and draws a parallel coordinate plot based on it. In the following figure, which is the famous Fisher's iris data, the data consists of 150 cases and with 5 variables. The first variable shows the label. So the first variable is categorical, and which has 3 labels, setosa and so on. And the other 4 variables are continuous variables. And so, and the problem is to find a good scaling of the continuous variables and also how to define the quantification of categorical variables. And this is a detail of the textile plot. Today, for simplicity, we only consider continuous variables, so the data real valued variables. So let me assume a data is given. The data is X is a matrix of the size n times p. The textile plot outputs a transformed data YTI, where AI is the location of the transformed variable and BI has the meaning of scaling. And the AI and BI are determined by the solution of the following minimization problem. This is a minimization problem. And the objective function means the difference from the horizontal line. And the restriction are the linear transformation of each variables, and the sum of all squared variables is fixed. And this slide shows the meaning of the objective function. The line graph, yt1, yt2, and so on, and also I drew the average of these 5 variables. And the objective function measures the difference of these 2 line curves. And so the result will become the line with close to the horizontal line, and so on. And in this talk, we focus on the output matrix Y. So the output of the textile plot. And it is not difficult to derive, to prove that the output matrix Y satisfies the following 2 conditions. The second one is obvious because it is contained in the restriction of the minimization problem, and the first one is characterized by some eigenvalue problem. And so we define the textile set, which is a set of all matrices Y satisfying these 2 conditions, and we denote it by T sub NP. And we want to understand the shape of this set, or we want to understand this set, the subset of matrix space. And I have to note that these 2 conditions are necessary for the output of the textile plot, but it is not sufficient. So I will discuss later about these sufficient and necessary conditions. Okay, and we first point out that the textile set just defined in previous slide is an inverse image of some differential map defined below. Let me denote the gram matrix of Y by this one, function G. G of Y is just the product of transpose of Y and Y. Then it is, of course, it is a positive semi-definite matrix. And also define another set T plus P, which is a set of positive semi-definite matrix satisfying these 2 conditions, corresponding to the 2 conditions in the textile set. So the first theorem is the textile set is given by the inverse image of T plus P with respect to the function G, the function outputs the gram matrix. So the following picture shows the relation of these objects. The textile set is denoted by T sub NP, and the map G is here. So the map G maps real matrix Y to the positive semi-definite matrix G of Y. And we also defined T plus P in the space of positive semi-definite matrix, and then the theorem says the T and P is the inverse image of the T plus P. The proof is very easy, not difficult. And then as the next topic, we define the strict textile set, which is a proper subset of the textile set. And let us recall the condition. This one, this is the first condition of the textile set. And so it is easy to, not difficult to see that the lambda here is one of the eigenvalues of the correlation matrix defined by this one. But in the original definition of the textile plot, this quantity lambda must be the maximum eigenvalue of the correlation matrix. So this condition is, I said, this condition is necessary but not sufficient. And at this time, if y is element of the textile set, then the lambda in the previous slide here, lambda is the maximum. So lambda is the maximum eigenvalue of the correlation matrix if and only if this matrix Q is positive semi-definite. This matrix itself is not necessary to be positive semi-definite, but if this quantity is positive semi-definite, the lambda is the maximum eigenvalue. So we define the strict textile set by strict textile set is the set of matrix Y such that the matrix Q defined by this one is positive semi-definite. Sorry. And again, the matrix Q depends only on the gram matrix, so we denote it by Q of S, like this. And we also define the set T plus 1P by the intersection of T plus P and the matrix S with the property that QS is positive semi-definite. Then the strict textile set is given by the inverse image of T plus 1P. Here is the image of the relation between these objects. So T sub NP is the textile set, and T NP1 is the strict textile set, and they are inverse image of the corresponding objects in the space of positive semi-definite matrices. And then we notice that there is some subset A here in the space of S plus P, and which is defined by the inverse image of Q. And we will see two examples of A, two examples of P. In this slide, I show the set A in the case of P equal to. If P equal to, the matrix QS is given by this formula. So the condition Q of S is positive semi-definite is obviously equivalent to this quantity. S12 is non-negative. So in the two-dimensional case, the set A is given by this one. For the three-dimensional cases, by a similar calculation, we obtain a necessary and sufficient condition to be the set of necessary and sufficient condition for a matrix S is in the set A. But for high dimensional case, it is not easy to obtain explicit formulas, but we can show that the set script A is a convex cone in the space of S plus P. And also it has an interior point in the space, in this space. And because if we define the script B by the inverse image of A, then also we can show that this set B has an interior point in the space of this one. We have to note that the textile set itself does not have interior point, which is a low-dimensional object. Okay, so in the rest of my talk, we quickly demonstrate that the textile set consists of regular submanifolds. And furthermore, we obtain an envelope of the textile set and a canonical form. This work is motivated by Inselberg's paper. So our observation starts with the quantity lambda in the equation, which is the first condition of the textile set. If y is the output of the textile plot, so if y belongs to the textile set, then this lambda is bounded as follows. So lambda is greater than or equal to 0 and bounded from above by p. And the two extreme cases correspond to these kind of degenerated case. And so if we define a subset, if we define the function f lambda by the right hand side, then by definition f lambda inverse 0 yields a classification of the textile set. So the textile set T and P is a disjoint union of these sets. And for the third theorem, this theorem says that f lambda inverse 0 is a submanifold of codimension p plus 1. So because the textile set consists of these the textile set is decomposed into the set of f lambda inverse 0. So the textile set consists of these p and p minus 1 dimensional submanifolds. And we also found that the textile set, if n equal p, the textile set is inverse, included in this set inverse image of f lambda. F lambda is defined by this one. And because this function is quadratic form, so it has the canonical form by using by using some linear algebraic tool. So the canonical form of this envelope of the textile set is given by this formula. Okay, so let me summarize this talk. In summary, we investigated the textile and the strict textile sets by using differentiable maps, which are the inverse image of some grammar metrics and so on. And we also elucidated differential geometric properties in the last part of the talk. So future works are to define appropriate metric for the textile set, and I'd like to also investigate the probabilistic properties of y and gy if the original data x is distributed according to some known distributions like multivariate normal distribution. And thank you very much.